Good day, Dr. Michael, Dr. Isala, and all my fellow classmates. We are from Group 2. Now we are going to present our project assignment, MOSFET scaling. Before that, I would like to introduce our group member, Jason, Kinsian, Jonathan, and me. Let me introduce MOSFET first. It is also known as metal oxide semiconductor field effect transistor. It is used as switching and amplification purposes in electronic devices. It has 4 terminals: drain, gate, source, and buck. One of the important parameters of MOSFET is channel length. The shorter channel length can increase the operation speed and reduce area of the die. However, if the channel length of MOSFET near to the space charge regions of source and drain junction, then short channel effect occurs. The first short channel effect is drain-induced barrier lowering, also known as punch-through effect. This is because drain to substrate space charge region extend completely across channel region to source to substrate charge region. As a result, no barrier between source and drain. Then, large current exists. The second effect is impact ionization. This is because in short channel MOSFET, charge carriers get higher electric field. Then the charge carrier gains more energy. It collides with other atoms, generates electron-hole pair, and causes avalanche effect. The third effect is surface scattering. This is because mobility of carriers in short channel MOSFET decrease. Higher gap to source voltage is required to turn on the MOSFET device. Here shows the ID versus VD curves of device 1. It shows that at higher VG, then the ID also is higher. From the surface charge to gate voltage graph, it shows that the carrier concentration for VD at 1 volt is lower than VD at 0.05 volt. The next is ID-VG curve. The threshold voltage when VD equals to 0.05 volt is 0.25825 volt. When VD is 0.1 volt, threshold voltage is 0.0963 volt, which can conclude that at higher VD, the threshold voltage is lesser. The IF for VD equals to 0.05 volt when VG equals to 0 volt is 1.9399 times 10 to the power of negative 8 ampere. While the ion at Vg equals to 1 volt is 0.00135 ampere. The IO for Vd equals to 1 volt when Vg equals to 0 volt is 1.1508 times 10 to the power of negative 6 ampere. While the ion at Vg equals to 1 volt is 0.00335 ampere, which is higher than when Vd equals to 0.05 volt. The DIVL for this device is 0.17047.
Hi doctor, I'm Jason. I'll present result of device 234. First of all, here is the graph for 3 devices. We can clearly see that the graph is proportional until one point, then become more flattened. From the graph, we can see that when VD equal to 1.2 volt, the ID is the highest. Next, these are the graph of surface charge VG's characteristic. We can clearly see that the graph having similar graph, which is a V shape. These 3 devices have lowest of carrier when voltage almost 0.4 volt and also 0 volt. Furthermore, here is the graph of ID-VG. From the graph, we have 3 similar graphs for 3 devices. The ID increase proportionally with VG until certain point, then it become more flat, where ID change not much but VG still increase. Lastly, here is the calculation for device 2, 3, and 4. We can find VTH value from the graph when ID equal to 10 to the power of negative 5 and VD equal to 0.05 volt and 1.0 volt. Also, the value of ID when VG equal to 0 volt and VG equal to 1 volt. For DIBL, we divide the differences between the VTH when VD equal to 0.05 volt and 1.0 volt, with the difference between the VD equal to 1 volt and 0.05 volt.
Hi, my name is Jonathan, and I'll be showing the simulation results for part 2, which is device 3 with tungsten gate instead of N+ polysilicon gate. So I will also be showing the simulation results for device 3 with N+ polysilicon gate here as comparison. So first of all, let's look at the IDVG graphs for these two different gates. So using 0.3 volts and 1.2 volts as our reference points, and at gate voltage of 1.2 volts, we can see that there's a difference of approximately 2 milliamps for N+ polysilicon gate, while for tungsten gate we can see a difference of approximately 1.5 milliamps. Next, let's look at the surface charge versus VG graph for these two different gates. So we can make a smart guess that device 3 with N+ polysilicon gate will have a lower threshold voltage than device 3 with a tungsten gate. Finally, here we have the IDVG graph for device 3 with N+ polysilicon gate and tungsten gate. So there are a couple of attributes of the MOSFET that we can extract from this graph. So first of all will be the threshold voltage in the linear region, which is 577.5 millivolts, while in the saturation region, the threshold voltage will be 157.89 millivolts. Now in the saturation region, we can also extract the leakage current, which is 1.8 microamps. Now in the saturation region, we can also extract the on-saturation current, which is approximately 3.42 milliamps. Now finally, we can calculate the DIBL values from the different threshold voltage in the linear region and in the saturation region. And the DIBL value is calculated to be 441.69 millivolts per volt. Now let's discuss on the simulation results for part 1. First of all, let's look at the leakage current for the 4 different devices. Device 1 having only 1.15 microamps, device 2 having 30 times more leakage current compared to device 1. Device 3 and device 4 are having much higher leakage current. This could indicate a problematic design because this means that during the off state, device 3 and device 4 are consuming large amount of power due to the large amount of current flowing through them. Now for the on-saturation current, we can see that there's an increasing trend in the saturation current as we move from device 1 to device 4. So these two graphs together indicates that device 1 is actually having the best power consumption performance, followed by device 2, followed by device 3, and finally device 4. Now let's look at the DIBL values for the 4 different devices. DIBL stands for Drain-Induced Barrier Lowering Effect, which is able to tell us, number 1, how much is the threshold voltage being reduced, and number 2, how severe is the punch-through effect. Because in literature, punch-through is sometimes referred to as a subsurface DIBL. So let's look at device 2 up to device 4 first. So we can observe that there's an increasing trend in DIBL from device 2 to device 4. And from the threshold voltage graph, we can see that there's a decreasing trend in terms of the threshold voltage from 0.16 to negative 0.289 and finally negative 1.06. However, we can see that moving from device 1 to device 2, there's actually an increase in threshold voltage due to increase in the substrate doping concentration despite the reduced oxide layer thickness and reduced channel length. So the increase in substrate doping concentration is actually more prominent compared to the reduction in oxide layer thickness and reduction in the channel length. So the DIBL values here, we can also see that there's actually not much increase, and this effect is being overcome by the increase in substrate doping concentration. Thank you.
Hi, Kinson is here. I would like to talk about second part of discussion. So basically, polydepletion effect is a depletion layer formed in the gate polysilicon layer next to the gate dielectric when the transistor is in inversion. The polysilicon depletion effect will result in an unexpected reduction of the threshold voltage, which will increase the leakage power. In the part 2 simulation, we change the N+ polysilicon gate electrode of device 3 to tungsten gate electrode. And from the simulation results, in IDVSVD BG graph, threshold voltage increases from 110.45 milliwatt and negative 289.95 milliwatt to 577.5 milliwatt and 157.89 milliwatt when the VD equal to 0.05 watt and 1 watt. Besides, in the IDPS-VD graph, off current of tungsten gate electrode are 66.3 nanoampere and 1.21 milliampere when off VD equal to 0.05 watt and 1 watt, which is about 93.97% and 58.96% lower than the polysilicon gate electrode. This proves the leakage current can be reduced when threshold voltage is lower, and hence it proved that the metal gate electrode with high K dielectric is preferred over polysilicon in variation of threshold voltage. In the conclusion, so all 4 devices are simulated successfully. We know that the short channel length results in charge sharing between drain source and gate, and this will reduce the threshold voltage by shifting it in negative direction. The DIBL explained the ID increases when VD increases. Apart from that, low channel doping and higher oxide thickness can scale down the threshold voltage, and it will result in the punch-through effect. One of the features that a good design should have is high threshold voltage. As we know, when the threshold voltage increases, off current, which is the leakage current, will be increased also. Hence, the power consumption of the device will be higher. Lastly, the metal gate electrode with high K dielectric version can avoid the polysilicon depletion effect. Thank you.